Well, I'm going to start so we can go to eat, right? And it's always very hard to speak about Dan Kleppner because he doesn't need transparency, he doesn't need topic to speak. And we need to start setting the topic and go on with it. So the idea of this, the lectures of today, except Wolfgang, is to give some introduction to the topic, because we know that not everybody works in this field. And we are speaking about laser cooling all the time. We are speaking about quantum gas all the time, and I'm sure that all the speakers will be telling you about optical lattices and scattering length and everything else. And so we thought that those lectures supposed to provide you the fundamental or the basics of those concepts. And so that's why it's called Fundamentals of. But in fact, and if you don't know me, I'm Vanderlei Bagnato from University of São Paulo. And we have a center there. And one of the topics that we are involved is quantum gases. Okay. And so I prepared an outline that goes like, first would like to give you some ideas about laser cooling and trapping. I know that today they don't even tell you how they reach the temperature they need and how things stay confined in the potential and how the potential change things. But so we'd like to just review some of the things about cooling, trapping, and some of the main concepts that you'll be hearing about on the lectures that may be important, like optical lattice and so on. Normally, laser cooling is being around for long, and I guess that almost everybody already hear about laser cooling. They have a good idea about momentum of light, and even in the basic courses of physics, we teach that, right? We always teach about radiation pressure. So this is a concept that most part of the people, they have already. But evaporation, which is much older than laser cooling, is a topic that normally people don't cover so well. And then there are a few reviews around. And I took one of them, which I like very much when I read. That's the one that was written by Wolfgang Ketterle and who is the other co-author? I forgot that. No, it's not the Varena, it's the Advances in Atomic and Molecular Physics. Yes, that's right. And so I will speak a little bit about evaporation and taking an approach that was taken in this. I'm going to mention the review. I don't remember if I put all the authors in. Which is a scaling approach. How the quantities of interest varies during evaporation, and how can we win, and when are we losing? We're losing more atoms than we are getting density and temperature lower. Then I want to give you the concept of optical lattice, because most part of the talks will be in optical lattice. Okay. Then we're going to say a few words about atomic interactions, at least define what is the scattering length and the importance that scattering length has for the field of quantum fluids. Then I will start the fundamentals of Bose-Einstein condensation. I think I prepare more than what I'm going to tell you. Just calculating a few properties, like the order parameter, which is the accumulation of atoms in the ground state. What's the dependence with temperature for a generic potential type, and how is the spatial distribution comes out. Okay, so how we calculate that also. And I'm going to use here an approach that's looking things in a semi-classical way or looking things in a phase space. And of course, I'm always going to illustrate with some things in the lab, giving pictures, how is the experiment, how is this and how is that. And then I want to, in the second lecture, I want to speak more about the interacting quantum gas You'll be seeing the Gross-Pitayevsky equation many times. You'll be seeing Thomas Fermi approximation many times. So I want to tell you how the Gross-Pitayevsky equation comes out, what it means, and how can we solve it. And what is the other approximations we use, like Thomas Fermi. What is Thomas Fermi? What we get out of the Thomas Fermi approximation, right? And then there are some complements, which I think is the most important part of it, which is the Bose gas in a lattice. You know, I think Wolfgang is going to be speaking about some of this. And people normally put atoms in a lattice, which is an array of potentials, and they put all the atoms in the ground state of those individual wells. And then adiabatically, they take that away. And the question is, are we still with a degenerate gas at the end? So this is a question that people ask when they start to do lattice. But it would be nice for us to go and calculate for what kind of occupation in an optical lattice we still have a quantum degenerate gas at the end. And I want to tell a little bit about healing length, which is a word that's almost everywhere, but sometimes we just forget what it is. And so I'm going to speak about this. And talk a little bit about Fermi gas in a potential and make some analogies with Bose gas. Okay? Again, this is in the spirit of a tutorial. If you know everything already, which I know that a lot of you knows more than this, just relax, enjoy, okay? You can always ask a question that is easy to find a question that I don't know, and I will be not, I'm not going to feel bad. I'm just going to say, I don't know. So everything I'm going to tell you is in a review paper that we wrote some time ago, which I distribute. And those lectures will cover the first, this is a long one, it's more than 100 pages, but we're going to cover something like the first 20 pages. And so this is the idea. And a good point to start here is to just show, I mean, how can we make and how can we probe a quantum fluid? And I'm going to stick myself more to Bose gas, but normally the ideas work as well for Fermi gas. And Wolfgang and many others will cover in details the Fermi aspect of this. And but in general, when we want to reach quantum degeneracy in gases, the only way of doing that we know up to now is cooling, is reaching very low temperature, because as you know, that is this thermal de Broglie wavelength, which is an important parameter that tells us, when compared with the interparticle distance, when things should happen. So this is a kind of thermometer that tells us if the picture of a classical gas works fine, or if we cannot work in that picture, we have to go to the quantum picture. So, and the only way we know how to do this is, it would be nice if we could decrease the particle interdistance to reach this point where the de Broglie wavelength is about the interparticle distance. But, you know, if you start to compress a gas, some other kind of phase transition due to interactions takes place. So the only way that people found around is cooling down. Cooling down so we can still reach that regime in a not so high dense gas. And that's why we call a diluted gas. Okay? And the way of doing this is, as you know, normally you start with a gas, it's hot, like hell. And we have to remove velocity. And to remove velocity, sometimes we have to start by decelerating the atoms, producing a sample that is low velocity. So I'm going to just review this process very, very fast. And then once the R is low, or if you can work with the slow part of a thermal distribution, we can manage to produce what we call a magneto-optical trap, which I think was one of the great inventions for this cooling business, because it's a practical way of starting at room temperature and in a fast time reaching very low temperatures on the microkelvin regime. Then that's not good enough. You have to do a little more. So you do molasses, which is basically something related to magneto-optical trap, but in the absence of field. Okay? And all this has limits, which I would like to explain in a very tutorial way how they are. What's the limit temperature one can get in those processes. And then comes magnetic trap. When we start this part here, light has to be off. So there is no more light. But the things are not cold enough. So then comes the evaporation. And evaporative cooling is a key cooling technique in this business of quantum fluids. Without evaporation, forget it. We could never get there. We can keep the atoms trapped by light somehow, but we cannot reach what we need without evaporation. It would be nice to have a full optical scheme, and people are talking about for some atoms that they could eventually reach there, but so far we have no demonstration of a complete optical cooling down to the quantum degeneracy. So then comes evaporation, and when you evaporate, of course, everything up to here you can do without interaction. Ideal gas works fine. But when you get to this point, interactions are very important. And when you evaporate, interactions are important, as I said, and they manifest themselves in two different ways. Either particles attract themselves effectively, or they repel each other. And depending on what branch I go, I either produce a stable gas in the quantum degenerated regime, and then when I go here, I can drop this in an optical lattice. I can do atomic optics. So I just liberated this gas and it has coherence on it. And you can do nice interference and everything. I can study excitations like vortices and many others. And it's a big list of things you can do. Or if it is attractive, effectively attractive, I in fact have a kind of metastable system. For some number of particles, is unstable. And then, of course, it's also interesting things that manifest here. And if I have a fermion system, I do evaporation, and I can also reach a degenerate gas, which has all the Fermi properties. As you know, you have the Fermi sea, and you can study many things there, including the formation of pairs and everything that will be explained to you in other talks. But quantum fluids, maybe this was the first transparency I should put. Quantum fluids, it seems to be interesting because, it covers many, many fields. I mean, it's very hard to find a field now that doesn't cover. Maybe like Dan Kleppner shows the brain. So maybe sooner we're going to discover that quantum gas is important to understand the brain. I don't know. Of course, up to now, it's keeping the brain very busy. And, but it covers thermodynamics as a phase transition, right? It's very interesting. It covers quantum mechanics as this coherent wave of matter, which is the main object of quantum mechanics. Here we have seen by eyes. It covers quantum statistics. You know, if you study quantum statistics, you see that the occupation of the cells in phase space is the important feature in quantum statistics. And here we have a good example of this. Quantum field theory as a spontaneous symmetry breaking. That is a good example and an important thing to be investigated. Condensed matter, all those transitions from superfluid to isolating and even superconductor kind of understanding and everything can be done. Nuclear physics as a many-body type of effect, like the three-body type of effect that Wood-Green recently, 2 years ago, I think, published a very nice paper that by the first time they observed some many-body effects in atoms that is very pertinent to nuclear physics. And so on. I mean, you could name it, and as I said in the beginning, there is an article in Physics Today that produced a very nice diagram in where these Bose condensation and these quantum fluids are affecting in understanding. And without speaking about laser theory and everything else that, you know, now we can do coherent beams of matter and understanding this too. So this is involved in many fields. So the importance comes here. So I'm going to start by this deceleration, and as you know, I'm going to do a lot of hand waving type and shaking and explaining. But in many cases, you have to start with the atoms in a beam, and then you have to decelerate them to have like a slow motion beam to start the process, to trap them by light and then cool further and then trap by magnetic field. And in fact, this was one of the first demonstrations of laser cooling. And the idea is very simple. You have atoms moving, you shine light against the motion. And if you are smart enough and do a good engineering, you can manage the atoms to absorb many, many thousand photons. Each photon transfers a tiny little momentum, but if you make it to absorb many and many, you can just bring an atom that is normally to room temperature or above 1,000 meters per second type of velocity to almost rest, to a few centimeters per second. And the way that this is done is by the radiation force. And the radiation force is basically the momentum of the light, which is h bar k. K is the wave vector, which is 2 pi over lambda in the direction of propagation, times the rate of transition, times this factor here, which is basically the probability of transition, which depends on the Rabi frequency, which is the intensity of light. It's related with the intensity of light and the capacity of the atom to absorb this light, divided by the tuning. This gamma is the natural line width, which is also the rate of transition, right? So this is a well-known expression for the radiation force, and delta is the detuning. But if delta, when you start to make this atom to absorb light, very soon the atoms absorb enough to Doppler shift out of resonance. Is? No, you can deduce this relation, right? If you look in the notes I hand out, there are many papers on the 90s and on the 80s calculating this radiation force in a very detailed way. So that's not empirical. I mean, it's well done. If you treat the two-level system and you couple the internal degrees of freedom of the atoms with the external degrees with our motion of the center of mass, you can come with the radiation force that acts on the atom. But here the problem is that this number here, when the atoms start to absorb photons, it starts to decelerate. And if the light has a fixed frequency, the atoms start to see by the Doppler effect a different frequency. And then, you know, if I manage to set my laser frequency, which is represented here by this detuning, for some velocity, very soon this is no good anymore. And people already realized that long ago, and they said, well, to really bring from 1,000 meters per second to 1 meter per second, which means a lot of photons has to be absorbed, I have to keep the atom seeing the light during the whole process. And there are two ways of doing this, but both correspond to adjusting the frequency of the laser during the process. And one which is a very good one, and we use it, is what they call the Siemens Tuning. This detuning, if I have the atom in the presence of a magnetic field, the detuning is not only the difference of the two levels of the frequency of the atoms and the light frequency. It also involves by the Siemens shift, involves the magnetic field and the Doppler effect as well. So in fact, the detuning that the atom sees is a combination of the detuning in the absence of motion and absence of field, plus the effect of the field and the effect of the Doppler effect. And this creates a very interesting situation because I have something here that depends on B and depends on V. So if I create in the space a magnetic field that compensates the spatial variation of velocity, I can keep delta constant. during the whole process. And then can make the atoms to absorb many, many thousand photons without getting out of resonance. And this is the basic idea of what we call the Siemens Tuning technique, which producing a magnetic field in space with some special variation. I just come here and demand that this is a constant. If I demand that this is a constant, and I say I want also a constant deceleration, means that velocity will vary following this rule here in space, right? With some fixed deceleration. I come with what's the magnetic field in space that I need to build so that an atom gets in here, that is the light shining, and atoms follow this and get out in a very low velocity. So normally, this picture I have here, shows that atoms start the process. Let me change color to show because this was first done by sodium, right? With sodium, which absorbs yellow light. So atoms start in here, and then the field matches the velocity, and then they start to decelerate, and decelerate up to the end. So you leave this process in a very low velocity. You can go on and, atoms can only absorb and emit photon in some finite rate. So you can come as an exercise as a problem set. Okay. You can consider this force and ask what is the maximum deceleration one can have. And you're going to see that that's produce some limitations on the field you can build. Okay? And this is what we call a diabatic falling of the atoms in this field. And normally it's a very good thing. You produce a magnet like this. You inject a beam which has a broad distribution and comes out a beam with a very narrow distribution. So this is a cooler in a beam. You introduce a hot beam, comes out a cold beam. Okay? And of course, there are limitations where you can get and everything, but this is an important technique. Without this deceleration, at the beginning, you could not really reach condensation in sodium atoms, for instance, which are to produce the vapor, you have to heat up the metal, and then you produce a very hot vapor, and you have to use this technique to produce what you need. So this is the deceleration, and Bill Phillips got Nobel Prize by studying and developing this, and everybody around the world uses, like we do in São Carlos. And that picture you saw here, oh, not this. This is the end of all the decelerator we had, and you see the yellow light here. So basically, about here, a beam starts at 1,000 meters per second atoms, and they come, and this yellow ball you see is the beam stopping. So here, atoms are at a very low velocity. And of course, we do some little tricks, and we let a little flux of slow atoms coming out to be able to capture. Okay, so that's for deceleration. And normally, this is the first step we have to do. Now comes the Magneto optical trap. And the Magneto optical trap is something very interesting, but only works at very low velocity. And it's very simple. You have an atom, you shine two lasers, opposite. And as you know, when the atoms start to move this way, the atom sees this laser bluer and this one redder, right? And vice versa. So what I do then is the following. I go and see that the atom has some internal structure, and I set my lasers red tuned to those transitions, such a way that when the atoms, so those lasers are red tuned, when the atoms start to go that way, it sees this laser bluer, so gets closer to resonance of this, but farther from resonance from that. So the probability of absorptions always is greater for the laser that counters propagating the motion. So as a net result, you have always a force against the motion. And if I am smart enough, and if I use the polarization and selection rules, I can produce a restoring force, not only a force against the motion, which is a kind of damping force, but I also can produce a restoring force So I can produce a point in space where the forces goes to 0. So combining this, if I consider the radiation force, and I make one minus the other, I can show to you that the effective force is a damping harmonic oscillator. And this damping part does not depend on the presence of a magnetic field, because it's basically based on the Doppler effect. So the atom has to see a different Doppler effect if you move into one side to or the other. And this part, which is a restoring force, like a spring constant, right?
Where are the losses?
What?
Where are the losses? Because you have stuff that is losing.
Where is the energy going? To the light.
But because of the Doppler effect?
Yeah. I normally emit a photon bluer than I absorb. So the energy is going, and you can ask about entropy. Always this question is there, right? What about entropy? If you remember that the laser beams has a lower entropy because all the photons are very well organized, and these atoms absorbing light and emitting light to everywhere, entropy is increasing. So we satisfy all the thermodynamics, everything. We have no trouble with thermodynamics. Right, Giacomo? Not here, right? We may have in another point. So then the overall force on the atoms is a damping harmonic oscillator. And if I don't have a magnetic field, I only have a damping force, no restorative force. And this is what we call optical molasses. That gave the Nobel Prize to Stephen Chu. Okay. And the idea of magneto optical trap came by David Preacher, mainly, together with other people, and but did not generate the Nobel Prize. But without magneto optical trap, we could not do anything that we'll be speaking in this school. Okay, so the idea then is just put two coils like this, create a gradient of field everywhere in space. We shine 6 beams, 2 by 2, counter-propagating, having having a well-established polarization to deal with the levels we want to deal. And the response is that I drop slow atoms in here, and I just capture all of them in a little ball. And this reaches temperature on the microkelvin limit. So this is my starting point for a lot of things. Normally, I decelerate a beam and drop the beam in this environment, this viscous confinement environment. If I don't have a slow beam, well, this is so nice that works even without the slowing beam. If I turn this in a vapor at room temperature, what's happened is the low tail of the distribution at room temperature is slow enough to be captured in this process. And if the process can hold the atoms, the system will rethermalize, put atoms back, and I keep accumulating atoms. So that's how powerful is the magneto-optical trap. And is also a starting point. And to tell you what's the limit we can get in here, I made a kind of in an easy way to understand how is this motion. And if you have any question, you can ask it to, where is Monica? Ah, it's there. She's the undergraduate that is calculating that kind of thing. So suppose you start with an atom, and you have only 2 laser beams. You can absorb one or the other, right? So if the velocity vector, or this is in momentum space, so let's speak about momentum vector, is here, by absorption, the atoms can come to point 1 or 2, because can absorb one from one laser or the other. So receives a kick in one of those directions. But then the atom emits, and spontaneous emission is random. So if you are here and you emit in any direction, you're going to end in a sphere around point 1. And the radius of the sphere is exactly the momentum of the photon, which is h bar k. If it is in 2, ends in a sphere around 2. Okay? So spontaneous emission, in fact, is a heating mechanism. It heats up a little bit because put photon in a random way. If I'm taking momentum only in the direction of the laser, but the spontaneous emission puts everywhere, this is a kind of heating mechanism. And if I want to write an equation on the balance of the kinetic energy of the atom, The time variation is the cooling part, right? Which is the velocity times the force. This is the power that is removed. But I have a heating term in here, which is due to the spontaneous emission. And how I calculate this heating? Well, I just come and calculate what is the average momentum an atom ends after absorption emission. And this is very easy to do, right? You have two spheres, which radius is h bar k, and I ask you what's the probability of being in some point. The probability of any point is equal, so you can calculate the average vector in these two surfaces. And turns out that the average is 2/3 of h bar k square. This is the average momentum square that you get after one cycle absorption emission if 2 beams are considered. But we can go further and consider 6 beams. Now you can imagine what's happened. You have 2 spheres here, 2 spheres here, and 2 spheres here. And the only work you have to do is calculate what is the average momentum that an atom can acquire after a cycle of absorption emission in the presence of 6 beams. And turns out that, and the force, I already gave you the expression of the force, which you can expand for low velocity, basically. And you can end with an equation for the variation of the kinetic energy, which is a very simple equation. And as you can see, you solve this equation, and you can find how the kinetic energy varies. Everybody understand me? Absorption, photon, so you always remove momentum in one direction, and you put in the others, but you end by having a final limit of the kinetic energy, which we call Doppler limit. Because you can't avoid this random emission, so that gives you a limit. It's like the average energy of the drunk guy going around, right? You can't stop. The drunk guy is always dancing. So there is a limit motion, right? This is what we find in here. And what is this minimum limit? Well, if you solve this equation, you naturally get what is the minimum limit, which is the limit of the kinetic energy for t goes to infinite, if you leave this on for a time. And this limit is given by this expression, right? That's depending on the frequency of the laser, depending on the type of atoms, basically. And then you can ask, oh, that is a minimum of the minimum? So can I work, if I want to get the lowest possible, I'm going to play with the frequency of the laser such that I reach the minimum of the minimum. So I take this minimum, the derivative with respect to the laser frequency, which is delta, and I ask, when is this 0? And I found that the minimum of the minimum happens when I'm tuned half away of the natural line width. And the minimum of the minimum is 3/4, the kinetic energy is 3/4 of h bar k, gamma. And that gives you a limit that for sodium atoms is 240 microkelvin, for rubidium atoms is about 140, for cesium atoms is about 120, for potassium is 150, for lithium is, oh, nobody works with lithium. For lithium, it's always around 100 microkelvin. The limit is in the notes for lithium too. Okay, but then when people went to the lab and they find, well, let's study this limit. They found that the limit wasn't there. The atoms reach much lower temperature. A factor of 100 sometimes lower. And then, Claude Cointanoudy and colleagues from École Normale in France came with this idea that, oh, wait a minute. When light interacts with atoms, it's not only momentum that's transferred. The level shifts. This is called the AC start shift. And in the presence of light, may have a configuration, and then things may change. This approach I just did together with Monica doesn't work, I'm sorry. We have to go even further. And so this limit is not the limit. And they understood this long ago. I mean, everything long here is 20 years, right? And they come with the idea of this Sisyphus Cooling, And the idea is simple. I mean, if you have a stand wave, two laser beams, and you work out the polarizations and everything, the level shifts. So you start to cool down. You're going to see that atoms, in fact, they lose energy climbing the light potential that are created on the levels. So, in fact, they found a nice situation where atoms start to move from the bottom up, and then they absorb and emit and comes to the bottom again. That's why the name is Sisyphus. So atoms lose energy because of the light shift, because they're always climbing the potential up. Okay, so this is what we call sub-Doppler cooling. So with sub-Doppler cooling, you can go much further down, and in fact, for sodium atoms that you remember, the temperature was 240 microkelvin as a Doppler limit. In this Sisyphus stuff, which is basically the limit that you're going to reach, it's basically dependent on the size of this barrier, of this well here, which is dependent on the Rabi frequency, the intensity of light, and the detuning of light. So for sodium atoms, when Bill Phillips did some experiments, was 2.4 microkelvin, very cold, right? And in fact, this one was one of the citations in the Nobel Prize that they got, that they beat the Doppler limit. Anyway, so that's mainly the ways we start by producing atoms in the microkelvin. Once they are cold enough, you can turn off the lights and build up magnetic barrier. And as you know, we work with a species which has this magnetic dipole. I think Dan Kleppner started to explain the magnetic stuff because he's going to get to this, to the magnet trapping. And if you don't know what I'm talking about, well, remember the spin of the electron. And if you remember the combination of the electron spin and the nuclear spin, you come with the hyperfine levels in the hydrogen. And you see there are levels that grows with a magnetic field, because in that case, the total magnetic dipole in there is opposite to the field. So atoms fuse a force towards the minimum of the field. So that's how we magnetic trap the atoms, using their magnetic structure. So if you have those atoms, and you produce a field which grows in space, and if they are in those levels here, you see, they're going to feel a force always to stay in the minimum of the field. And that's how we keep the atoms in the minimum of the field, in the absence of light. But of course, the Bohr magneton is very, very tiny, right? It's very small. You need a very, very large barrier, a very large gradient of magnetic field to keep an atom at room temperature there. In fact, if you want to keep an atom at room temperature which has a Bohr magneton, you probably need about 1,000 or 20,000 Tesla of field, which you know is hard to get, right? So the way of being able to trap atoms magnetically with the fields we can produce in the lab is to start with them very cold, because then their kinetic motion is compatible with the magnetic barrier, and we can keep them trapped in the minimum of the field. And that's how we magnetic trap the atoms. And there are many ways of producing those magnetic fields. A simple way is just having two coils carrying opposite current, right? If you have them, this is, you see the field is zero at the center, and in magnitude, in amplitude, grows everywhere. So this is a kind of minimum of amplitude of magnetic field, and because the atoms follow the field adiabatically, they are this low. That's why then we'll come with this Larmor and everything, and adiabatic following. He's going to show to you that even the field is varying in space. If it is in slow motion, it follows. For the atom, always the field is pointing in the quantization direction, and everything works fine, right? So we produce, this is in fact, was the first magnetic trap demonstrate, which was putting currents in two coils, and the overall amplitude of the magnetic field is this way, so you can see that's a parabolic field in two directions. No isotropic, because it's much stronger in the z direction than it is on the plane. But even though is a magnetic bottle that you can confine in particles. But there are other ways. Sometimes you don't want zero field. Also, then I'm going to explain to you, if I have a zero field, and those atoms, they have those structures. Where is? Oh. If I go to zero field, imagine my atoms is in this state, which likes to be in the minimum of a field. But if I reach the zero field, then it can suffer a transition, a spin flip, which is called Majorana Transition. It's Majorana, that's how you say? Majorana. The Italian guy, right? And then it can live in this state, which is not trapped. So sometimes to keep the atoms there without losing many, you have to avoid zero field. And to avoid zero field, people came with many, many different ideas. One of them is having coils like this and adding more coils here. And this is called the Yaff-Preacher configuration, which you avoid having zero. You have a minimum of field, but no zero. So you avoid those Majorana transitions. Okay? And this is one of example. If I put coils arranging this way, I end by having a minimum that I can trap atoms without having zero. I have to run. And normally, you have this, only these two coils would be a quadrupole. You add another one here. You end by some specific current in this coil compared to the ones in here. You end by having a minimum here that's not at zero. And then when you look to the trap atoms, this is the picture of Emmanuel. If you start to increase the current in this coil here, which is this coil here, you see the atoms moving from, this is a kind of quadrupole. The atoms are here. You see it moving until this is the evolution of the field. You join, and then this is the position where you want to be. And of course, the atoms are much spreader anyway than in the other ones because they just spread along this axis here. That's how people magnetically trap the atoms. And of course, if you have to decelerate and then trap, the system is more complex. Normally takes a full room. Nowadays, people produce a trap here, capture atoms, transfer the atoms, and work with them cold in another chamber. So all kinds of tricks is being done. This is a picture of our lab. This is how this looks like. You have atoms in here. They are coming this way. You have coils and other coils, and you're working here. How you measure so low temperature? Well, temperature for us is half of mV squared. This is temperature for us, right? And then we measure by measuring V squared, in fact. And we do one thing that's called time of flight. We trap everything, and then suddenly we destroy all the potential and see how long it takes for the atoms to expand. And that's a thermometer that can work it down to microkelvin. You can't stick a thermocouple there or thermistor or anything, unfortunately, right? So our thermometer is motion, and then we measure motion to get temperature. And this is a normal. This is the old experiment we had on sodium. This is a normal laboratory that those things happen. Once you put the atoms in a magnet trap, they are not cold enough. We have to go further down. And then we use evaporation. And evaporative cooling is an interesting cooling because it goes from, sometimes could go from millikelvin down to microkelvin or picokelvin, right? So it's a very nice technique that has many decades of range for you to play with. And goes much beyond the radioactive techniques. But to evaporative cooling to work, you need to have confinement. Atoms has to be there. If you let it go, doesn't evaporate so well. And needs interaction. And the reason that needs interaction is because evaporation works in the following way. You have a distribution of atoms as a function of energy, right? And that's determine the temperature. If I come and cut an edge in here, if I produce a cutoff and let the atoms with some energy above go, they go. But the rest of it is not in equilibrium. It will thermalize. And the way of thermalizing is redistributing the energy so that some of the atoms will populate the tail that you remove. That's how evaporation works. But for populating this tail, of course, atoms have to talk to each other, and then you need interaction. So evaporation doesn't work in ideal gas. You need to have interactions. And if you want an easy scheme, you start with an initial distribution. The number of particles is the integration. Imagine that G is like a Maxwell-Boltzmann distribution. If you integrate all the energy, you have the number of particles. If I remove the ones that are above some value, then I'm left with a number that now goes the integration from 0 to this cutoff. Now, this new number gonna rethermalize and gonna produce a new distribution that I call G1. And this G1 is now, the new temperature is given by integrating this G1 from 0 to infinite. And of course, this temperature has to be lower than the original one. So that's how evaporation works. And then I move the cutoff. Move. I go down, down, down. And you already realize that evaporation means losing atoms. There's no other way of taking energy off the system. Atoms will carry energy away. And that may be a problem. I can't stay at 0 temperature with 0 atoms. Doesn't help. So I have to play well so that I end close to 0 temperature, but with some atoms. So the analysis that I'm going to make involves, well, first of all, we want to be efficient in here. We want to lower down the temperature with the minimum cost, which means losing as minimal as possible, losing as few atoms as possible. But of course, I have to have time to do that, and I have this sample there. It seems very easy to keep the sample there forever, right? I turn on my machine and I go there, they are there. They are trapped, but they have a lifetime because they collide with non-trapped atoms. They do all kinds of things, and I lose atoms even if I'm not evaporating. And this technique has a limitation. You know, I must evaporate faster than my atoms goes by any other reason. And this any other reason involves analysis of two types of collisions. The good collisions, which are elastic collisions. Elastic collisions cannot remove my atom out of my trap if they are among those atoms. But there are bad collisions, heating processes, and inelastic processes that remove atoms or heat them up. Those are the bad ones that I don't want. And it's the ratio between good and bad collisions that determine the success of my evaporation. And my final goal is to increase phase space density. Phase space is how many particles I have per de Broglie wavelength cubic. And when this is unit, I'm close to quantum degeneracy because the atoms are no farther than 1 de Broglie wavelength. If that is too low, I am in the classical regime. So the idea is cooling down to reach high phase space density. And I'm going to start by giving you the phase space density formula. If I have a gas with a density n and a temperature T, you remember that the thermal de Broglie wavelength is h divided by root square of 2 pi mkt. This is the thermal de Broglie wavelength. And the density times lambda cubic is what we're going to call phase space density. And you know, it's proportional to density and is inverse proportional to the temperature to the 3/2. And the goal here is, I have a high number at high T. After evaporation, I'm going to lose number, but I want to reach high density and lower T. High density and lower T. Everything works to increase phase space density. So my goal is not have a very high number. Of course, if I can work with a high number, it's not bad, right? Especially in São Carlos, which we have problems with the number. But the idea is having this high and this low works in my favor. So the main purpose of evaporation is reach high density, lower temperature. And how are we going to analyze this? I'm going to do an analysis, which I hope will not be so heavy for you, which involves scaling. We want to know how things works. How many atoms I'm losing, how much temperature I'm gaining, you know. But we're going to do that in a scaling way. And this is done by Ketterle and Van Druten in this Advanced in Atomic and Molecular Physics in '96, which I thought was a very nice analysis to do. And the whole idea here is we're going to start by, you know, all those things are logarithmic law, right? They always decay in time in exponential way, so everything is logarithmic here. So let's start by defining what we call relative temperature variation per particle that is evaporated. So if my temperature is changing by T dot, I divide by the T. And if my number of particles is decreasing by any dot, I divide with n. And if I take the ratio of these two quantities, I have this quantity which I call alpha. Okay? So this alpha, it means how much temperature I decrease per particle I evaporate. Okay? Everybody feels that? If alpha is constant, it doesn't need to be constant. I'm going to say alpha is constant. If alpha is constant, means that temperature scales with the number of particles following this law. You just multiply this here, you integrate everything in time, and then you have alpha logarithm of any t over any 0, which is the initial number, is equal to the temperature at some time t divided by the temperature in some time 0. It a logarithm is, I just put alpha, multiply, and I get the solution. Everybody follows me, right? So the temperature decreases with the number of particles following this scaling law. So the important exponent here is what is my unit variation, relative unit variation of temperature per particle leaving my system. Okay, so of course alpha depends on many things. And what I'm going to do, and Ketterle has done in his paper, is find out how all the things scales with the number of particles. That's why it's a scaling analysis. Okay. And of course, the particle has to be confined. We can put in a box, but I'm going to put in a power law potential. So my potential is proportional. This is not alpha, it's proportional. It's proportional to R to the cubic divided by delta. Why we wrote this way? You're going to see immediately why we wrote it this way. Because volume, you're going to scale with delta, which is the important thing. Because what I want, high density. So I'm going to investigate the number divided by the volume and find out when I'm winning that. So as you know, volume is depending on the temperature. If you take a gas in some temperature, 3/2 of kT must be equal to the potential energy. That more or less defines what is the volume occupied, right? It's the boundary. Everybody follows. Just the average energy is the potential. This defines the volume. So if I put it this way, you can see that the radius of this cloud confined scales with the temperature to the delta over 3. And the volume goes with R to the cubic. So volume scales with T to the delta. So remember, delta determines the potential. This is something I fixed. If it is a parabolic potential, linear potential, whatever potential I want, delta determines the potential. And the volume scales with the temperature of my gas that's trapped, as T to the delta. But the T scales with the number divided by with the number to the alpha. So I already know how the volume scales. And all the quantities we're going to see scales, I choose the number because number is the relevant number there. It's the relevant quantity. So this fraction, the number at some instant t divided by the number at the beginning is my parameter. Okay? And everything going to scales with this quantity to some x, which I'm going to determine now. You already seen how the volume is going to scale. X will be alpha times delta. So temperature, we already find, scales with N over N0 to the alpha. Remember, who is alpha? Is the relative variation of temperature by relative variation of number of particles. Basically, what's the decrease in relative decrease in temperature by relative decrease in the number by evaporation? Volume scales with V cubic, which is T to the delta. So the volume scales with the number of particles to the alpha delta. Okay? Just multiplication. How the density scale? That's the first important parameter, is the density. Density is number divided by volume. So I just take the number, divided by the volume, and the density scales with the number of particles to the 1 minus delta alpha. What I'm getting with this, you're going to see soon, because we're going to reach a place that we want to see if you are losing more particles and cooling, or we are losing more and not cooling. Basically, that will depend on those scaling. So the density scales like the density or the number to the 1 minus delta alpha. I can copy this and give it to you. They say that we have a Xerox machine here. We can run 100 copies. No problem. But if you want to take notes, it's good. So the phase space now. The phase space, remember, is density divided by temperature to the 3/2, right? Which is density times the de Broglie wavelength cubic. But I know how density scales. Is the number to the 1 minus delta alpha. And I know the temperature is just the number to the alpha. So this is 3/2 of alpha. So the density in phase space scales with the number of particles following this power law. Everybody's following me? Giacomo? Yeah. So this is the density of space. And this is the important thing we want to see in a few minutes. But I assume that I'm evaporating and nothing is losing. I'm just relying on the variation of the number of atoms. Now I want to introduce to you collisions, because I have good and bad collisions. Collision between atoms or among the atoms trapped, they are good. Collisions of the trapped atoms with the background, they are bad. Okay? So, what is the rate? How many collisions per time I have? This is we learn in the high school, right? The density times the cross-section times the average velocity. This is the rate of collisions. That's the first formula we learn when we learn collisions. Right? So this is how many collisions you have per unit of time. And I know how the density scales. The cross-section is the cross-section. They don't scale. It is what it is between two atoms. Now, the velocity, velocity is just the root square of temperature, right? It scales this way. So the rate of collisions, elastic collisions, evolves as a function of the number this way. Those are good collisions. We're going to introduce the bad collisions soon. So this has to be also fast. Otherwise, I'm trying to get, if this takes forever, evaporation will take forever. Okay? So this is necessary. And that's how the rate of collision scales with the number of atoms. Not with the, I already convert density and velocity in number of atoms. Okay. This is happening in the trap. Now we're going to evaporate. And to put the evaporation here, I have to say, oh, my potential is not infinite. It has a depth. And I'm going to characterize the depth of the potential by a parameter, this parameter, zeta. Okay? So this parameter here is the temperature times, the temperature times this parameter gives the depth of the potential. Of course, the depth is much lower than temperature. The atoms already left. So this parameter here, eta, has to be big, right? Otherwise, All the atoms are leaving. So we call this truncation parameter. And if you have a Maxwell-Boltzmann distribution in this trap, it's easy to calculate what is, if you have the equipartition theorem, you find that the average energy is delta, which is related to the potential, plus 3/2 of kT. This is the average energy. And of course, my average energy, this is this eta here is my top energy. Above this, atoms leave. This is the cutoff now. That's why we call it truncation. And what's the energy of an escaping atom? Well, it has to be above this, right? An atom with energy above this will leave. So if my truncation is this eta kT, eta plus a small k here, I was unhappy to put a k, but I tried to follow the same notation of Kittley. Otherwise, he will complain, but he's not present, so I could change it to another letter, because the k is also Boltzmann constant, right? But imagine this k here that I made so the energy of the escaping atoms, which is actually the energy that has been taken off, is the cutoff plus a little bit. Just a little bit. K is small. Eta is big, but k is small. Okay? Okay, so suppose that delta n atoms left in delta t. Remember, alpha is this quantity here. I just come in and calculate how much variation will be, right? So I took delta n, and delta t is the same for both, and then I cancel already. So this is the number of atoms that I have in here, and divide by this. So this is the first quantity here. And I already took in account the scaling law of temperature, divided by the number. So that means that alpha, which is the first constant, is related to everything through this relation. Is eta plus k divided by delta plus 3/2. What we learn here? We learn in the following. If this is less than 1, if this is smaller than the average energy, alpha is negative. Alpha is negative, I'm not winning. Okay? Alpha has to be positive. So that means that eta plus k has to be above the average energy. So I'm winning. So if you're going to set a cutoff for evaporation, the cutoff has always to be above the average energy. Am I making sense? So alpha, in fact, characterizes how much more than the average energy is removed by an evaporating atoms. Okay, so let me put the bad and the good collisions now. Suppose you have a density there that I'm calling N0. The rate of evaporation can be calculated the following way. Atoms with energy larger than this will leave, will escape. Remember, eta kT is the escaping energy. Evaporation rate. Now I'm going to calculate what is the evaporation, because see, the point here is the following. What atoms escape, for me to be in a good shape, I have to replace that atom. So the system cools down, understand? And to do that, I have now to compare the rate in which atoms are leaving with the rate they are colliding and replacing the atoms that are leaving. Understand? So first thing is, what's the velocity of an atom when it is in this cutoff energy? Oh, you know how to do this. Half of mv squared is equal to this energy. You already get what is the velocity of the atoms at the edge. Because that's the important guy. That guy left. I have to know what's the rate of collision there to replace it. Right? So that's the velocity for the atoms escaping with this energy. And if we consider a Maxwell-Boltzmann distribution, I can ask you, how many atoms has energy bigger than the escape velocity, the escaping energy? those are the ones that are going to go, right? And if you take the Maxwell-Boltzmann distribution and integrate from 0 to eta kT, that's the fraction of atoms that stays. From eta kT to the infinite is the fraction that is leaving, right? So, and if you calculate this integral, this is the fraction. If I have the fraction and if I have the velocity, I can come and say, well, the variation of the number is the fraction times the rate of collisions. Those are the fraction of atoms able to leave. And this is the rate of collision. So this gives me how many atoms are leaving per unit of time. So I come with this equation. Something is missing here. I think I forgot this eta. So it's missing a eta here. I'm sorry. Anyway, this n is proportional, any dot is proportional to n, and I can, this is all, everything here is constant. I set that. So I'm going to call this 1 over the characteristic time of evaporation, right? So in fact, this characteristic time of evaporation is this times eta times the, you see, when you multiply here, I forgot, pi cancels, but I have this exponential, and then I have an eta factor here, which is root square times root square, and I forgot. But I can now write here now. So there is an eta here. So the time of evaporation to the minus 1 is n0 sigma times the average velocity times exponential of minus eta times eta. So this is missing. This is the characteristic time of, if I normalize any dot by n, this is for one atom, right? Otherwise, it will be to 1 over e atoms, okay? Because if I integrate this, n over t will be n0 times exponential of minus t over tau evaporation, so, right? So this is a constant. I put n here, I integrate. This is a logarithm, and this is a constant. T divided by tau evaporation. Right, George? Okay, so now I have a time of evaporation. And I'm going to compare with the elastic time. Because if I'm evaporating in a time that's faster than atoms are thermalizing, I'm in trouble. And this will come out in a calculation in a few seconds. So the elastic time, which is the rate of collisions, is n0 sigma. And this root square appears because we'll be working in the relative frame. Then a root square appears, okay? So this is the average, and this is the relative velocity between two atoms. That's why I got a root square of 2. And the ratio of elastic to evaporation, I'm going to call lambda. 1 over tau elastic divided by 1 over tau evaporation is the ratio between the rate of evaporation by the rate of elastic collisions in the sample. I know I'm going too fast, okay? But I'm going to rend out the notes and you can follow. And this, if I substitute the elastic, which is this, and the time of evaporation with that one missing those terms there, you get this formula. So, what we're learning here is that the rate of evaporation divided by the rate of elastic collisions depend on the cutoff that I choose. Of course, if I put a cutoff too low, they're gonna just leave. It's not even evaporation. They just go away. There's no time for thermalizing. If I put this too high, then they only thermalizing, nothing leaving. Nothing's leaving from the trap. You understand? So this is a nice relation. But we want to go back to all the scaling that I did before. So now we're going to calculate the variation of the rate of collisions, the relative variation of the rate of collisions, which is, if this is varying, and everything is varying here, how is that varying? And this this quantity here depends on the evaporation and the trap loss. Why? Because if my density is varying due to the bad collisions, that quantity is also varying in time. If atoms are leaving, that quantity is also varying in time. And what is this quantity here? It's easy because I already know how density scales with number. And I know how velocity scales with number. I just take the derivative. This is just taking the derivative what I had before. And I end with this expression. This is easy derivative to take. Because I know how this quantity scales with the number of atoms, which depend on time. So everything will be taking the derivative of this quantity with respect to the number and the number with respect to time. That's why this term comes here. But I cannot forget the trap loss. So now I'm introducing loss, which has nothing to do with evaporation. It's something that takes atoms away without contributing to evaporation. So I have this expression, and of course, any dot divided by any is my definition of evaporation, my time of evaporation. So I have this expression here. And then I'm just going to progress a little bit and call the loss time, because I have a conventional loss, how many time it takes for a bad collision to take place, divided by the elastic collision. And this ratio is the ratio of good to bad collisions, right? If this number is big, means that I'm winning. If this number is low, means I'm losing. So we're going to rewrite the variation of the rate of collisions in terms of R. I just, I go back to that expression that you saw before. Here, I'm going where? I didn't mention this runaway evaporation. Runaway evaporation is a way that we're going to increase the density. We lose atoms, but we're winning by increasing density and lower temperature, okay? This is the definition of runaway evaporation. I put here as sustained by increasing the elastic collision rate, which means increasing density in the sample. So I'm going to rewrite this just in terms of the definition of R, because here I have evaporation, I have trap loss, and I define R this way. So I just write now everything in terms of elastic collision time, which is 1 over tau L. Wasn't there before. I introduced here, so that's why it's in evidence here. I define R as the ratio between the time of loss by the time of elastic collisions. 1 over R is the ratio between elastic to lossless collisions, right? Because the rate goes with 1 over tau. Okay, so I have this rate of collisions, and now you can see clear here that depending on the value of this guy, this will be negative. So it means that there is a minimum R below which I lose. So the rate of elastic collision decreases with time, and then I'm losing. Above this R, I win, because this became small, and then I have a good rate, which is the time increase of the rate of collisions. You follow me? So I did everything to show to you that the balance between losses and elastic collisions will be the determinant factor. So if I come here and put this to 0, this is my limit. Atoms are leaving, atoms are colliding, but I'm not gaining anything. You understand? Yes? The time of elastic collisions? Inelastic. Oh, that's depend on the background gas and depend basically on the lifetime of your sample. This is, for us, atoms in the background, that's the main time. Because, we have a good vacuum, but even though it's not perfect. So each 20 seconds, one atom is kicking my atom out of the, or in fact, each 20 seconds, maybe half of my sample is gone. So this is determined this time, which is the loss, right? You ask. The elastic is just determined by the local density and the cross-section and the temperature. So if I put this equal to 0, I come with the minimum I can have. And then the minimum possible R is obtained having 0 variation of the elastic collision rate. So that means that I have a minimum R. So this means that the number of collisions that are kicking atoms out, foreign atoms kicking my trapped atoms out, by the number of collisions taking place in my sample, has to have a minimum value. Below this minimum value, I lose. Above this minimum value, I win. Which means I increase the density, I lower the temperature, and the system are replacing faster than they are losing. Faster than they are going, sorry. So this is what I want. I want my system to replace the hot atoms faster than they are going. Then I'm winning. Okay, so with this number, now we're going to come and say, look, suppose I have a very good vacuum system. Take the losses away. So I have 1 over R going to 0. R is infinite. I have no bad collisions, right? So the time of bad collisions goes to infinite. Takes infinite time for a bad collision to take place. Then you come to this number, to this minimum, and you find that alpha has to be bigger than 1 over delta minus half. So in the approximation of no bad collisions, you have a limiting, or you have a relation between the potential you have and the rate in which the atom is going to leave, and how many lower temperature you get per atoms that leaves. This is necessary to sustain evaporation. So that somehow sets a limit on the rate that atoms are leaving. Now, of course, the maximizing the phase space density is the main purpose here, because that's what characterizes the quantum gas. And so I'm going to define gamma here as an efficiency parameter of evaporation. I'm almost to the end of this. And of course, gamma is the relative variation of the phase space density with the number. So it can be defined in this way, right? The time variation of the phase space density by the time variation of the number. I define gamma that way, right? And gamma, of course, the variation of the phase space can have evaporation contribution, which is good, and losses, which is bad. And the number of particles variation can also have evaporation, which is good, and losses, which is bad. And then this relation here, I just take the phase space that I calculate, take the time derivative, I end with this expression, which the losses here is 1 over tau loss, right? Which is the rate of losses. So I have this expression for gamma. And then you work out all the scaling I bought before, and you end by having gamma given by this expression. Why we have done this? Because we want to reach high phase space density as fast as possible. So we want to have a higher gamma. But if you analyze gamma as a function of your cutoff, which is in this expression, you find a plot like this. So the idea here is to work in the maximum, because that means I set off my cutoff in a way that atoms goes, and I increase as much as possible the phase space density. So the whole trick in the lab is to work always in this maximum. As the density varies and everything, you have to adjust your system to be in the maximum. Otherwise, you start to lose. And you're cooling the sample, but you're not building up phase space density. Was clear? Half clear? 20% clear? This is something that you have to do yourself. So I'm going to hand out this copy of this, and you take a look. But this is a very important point in producing quantum degeneracy. So even if you're a theoretician, you have to know that we have a lot of things to fight in the lab to reach the condition to produce the sample that you can go and calculate. Yes.
In the lab, you have to evaporate in some way. In this analysis, that method that you are using for doing the evaporation will is in the cutoff energy.
Yeah, normally you set up a cutoff. And you have to maximize this. You have to win the maximum possible increase in phase space density. Means you get a denser sample and colder. So that's what you want. Each moment you want dense and colder, dense and colder. And to do that, you have to play with the cutoff and always be in the maximum. Okay? This is what you have to do. That's why you have to adjust and only putting a cutoff and a rate, the cutoff comes down. That's the trouble we have in São Carlos, right? That's why we're having problem, right? So we have to manage to adjust everything. Of course, this is a theoretical analysis, but just show that if you don't do that, you don't reach what you want. Because you not always optimize. You have to work here to be optimized. So temperature decreases, but eta is fixed. Okay, this is eta. This is a number there that multiplied by kT give you the cutoff. Right? You understand? Well, that's depending on because you saw that the shape of the potential is here. So if you are evaporating a box or in a harmonic potential or in a linear potential, that will be different. The way to set the cutoff and the way to maximize will be different. Okay, so that's, well, I just want to say here before I finish that the light shift that I mentioned in the beginning can also be used to trap atoms, right? If you have this light shift, atom has to climb the light shift and fuse a force. Similar to what I explained about Sisyphus, we use that for trapping atoms too. And if you produce a stand wave with two laser beams that produce a potential well that varies in space, having minimum and maximum, minimum and maximum. And this is the basics of the optical lattice. It's putting light, and this light shift on the atoms produce the potential well. And doing that, combining, you can produce, oh, this is a bad picture. Do I have a better, yeah. So you can produce a potential in space, which have atoms. So you have a multiple wells in space in a regular periodicity by combining light beams. And normally they are detuned far from resonance, right? Because this light shift depends on that. So you want to be far. Otherwise, you transfer real momentum to the light and you have a spontaneous emission and you destroy everything. So you want to be in the situation where you have these multiple wells. And of course, these mimic a solid, right? And then you can start to study all kinds of things like tunneling between the potentials. You can start to localize those atoms, like in electrons localizing in an isolating system, or they can move freely, like in a superfluid, without dissipating energy or anything. And this system is a very important system for a lot of applications of this today. Okay, well, in the beginning, I think I just superestimate my ability of speaking fast, and I just couldn't do it. So I stop here. Now I want to give you atomic interactions and the fundament of Bose condensation and everything else. So you can see that the lecture of tomorrow will be very compressed and dense, like evaporation in phase space. So we're going to increase a factor of very big in the phase space. Well, why I spend a lot of time in evaporation? Because people normally don't expand it. They just explain evaporation is this and go away. And we evaporate. And we are finding out in our lab that this is hard. If we don't understand a little better evaporation, you cannot reach what you want. So I made this scaling analysis, and you already realize that everything is important there. The potential, the cutoff, right? And the ratio between good and bad collisions. And I think with this I will stop so we can go have lunch. And tomorrow I'm going to go a little fast on this because I know everybody's familiar with Bose condensation. So I don't have to define. I can just go to show you how we evaluate properties, right? And come to this part here, which I think, I'm sure my colleagues will go to Thomas Fermi approximation without asking you permission. So I better explain what it is and what are the limitations and how we work that out. If you have any question that I can answer, or if I cannot, good too. No? No questions? Oh, there was a few along the presentation.
Can we understand that bad collisions, that those that doesn't analyze the sample but only takes the atoms away from the trap?
Yeah. See, the analysis I made is based on the number of trap atoms. That number goes down with time. The question is, that number going down is increasing phase space density or not? So this is what I calculate. In some conditions, yes. In some conditions, no. In some conditions, atoms goes either by evaporation or by bad collisions, but you're not getting anything back. Right? In a terrible scenario, atoms goes and you end having the same temperature you start. So you didn't get anything. And not even got increase in density. So the analysis that I did show clear that a lot of balances are important to reach the evaporation regime where density and temperature, density is going up and temperature is going down in a way that you are getting orders of magnitude in phase space. And that's why evaporation allows you to start with some phase space density and get sometimes 6 order of magnitude. It's a very powerful thing if some requirements are fulfilled the past. Okay? So tomorrow I go on. I'm sorry that I will need, but I can rearrange things and speak about this. I consider this part very interesting because knowing adiabatic change in a lattice and everything, how that still keep quantum degeneracy and everything is an important thing. And so tomorrow we can delay and we're going to start sharp and end late. Thank you.